Good evening, my dear students. Hi, I am Vipin Mishra and I welcome you all in this foundation course on power electronics. This is going to be the lecture number 5 in which we are going to discuss harmonic analysis on both sides of converter, whether it is AC or it is DC. In power semiconductor, one side might be AC or one side might be DC. So what happens if the harmonics are there and how they are going to affect the AC side and the DC side of the converter. Also, we will discuss about some basic concepts of semiconductor devices, so that they will some basic concepts of semiconductor physics as well, so that they will help us in understanding the semiconductor devices like SCRs, diode, SCRs, diode, BJT, MOSFET and all others. So if we are comfortable with these basic concepts of semiconductor physics, we will be comfortable and we will be able to understand the large concepts of these semiconductor devices. So once again, I welcome you all in this lecture number 5 on foundation course of power electronics. So we are going to discuss the harmonic analysis and basics of power semiconductor devices. So in the last lecture, we discussed how we are going to calculate the RMS value, average value, and in different cases how we are going to calculate the power in any semiconductor or in any power electronic converter, we have to say. So we discussed that particular thing and we left by discussing the current distortion factor and total harmonic distortion. So we will start our discussion on today's topic from the same topic. So what actually are harmonic? Harmonics are basically the multiple harmonic terms of fundamental term. If they are there, they are going to pollute the quality of our voltage and current, or ultimately I have to say the quality of power. So harmonics, ideally they should not be there. If they are present, they are going to pollute the quality of voltage and current, or ultimately they are going to pollute the quality of power. But unfortunately, we are forced to have these harmonics when it comes to power electronics. Because of the switching actions of the converter, harmonics are there. Now when it comes to the power electronic converter, their input side may be AC or DC and their output side may be AC or DC as well. Now these harmonics are coming due to the switching action of the power electronic converter and they are affecting both the sides, whether it is AC or it is DC. What are the harmonics? Harmonics are the multiple frequency term with respect to the fundamental term. The fundamental term is all we desired, but we are getting some multiple harmonic terms as well. So what happens, how the harmonics are going to pollute the AC side of the converter? So we are first going to analyze harmonic analysis on AC side of converter. So let us suppose the case where we left yesterday, in which the voltage was sinusoidal but the current was a non-sinusoidal one. Means current is having DC term, current is having fundamental term, current is also having some other multiple frequency terms as well. So voltage and current, they are periodic, but the voltage is a perfect sinusoidal term of fundamental frequency, but the current is having so many harmonic terms. So what will happen if the current is having so many harmonic terms? So ideally we want a perfect sine wave, but if the harmonics are there, the perfect sine wave nature of this sine wave will not be there, and the shape of the perfect sine wave will be a distorted one because of the harmonics. Okay, so if the voltage is sinusoidal but the current is having so many other frequency terms as well, it might be having DC term, it might be having fundamental term, it might be having so many other terms as well. In that case, we may express this current. If I open this summation, I can express this as I naught plus I1 cos of omega t plus phi 1 and I2 cos 2 omega t plus phi 2, and so many other terms are also there. Now if I want to calculate the RMS value, If I want to calculate the RMS value of this current, then the RMS value of this current will be equals to I naught square. I naught is basically the DC term present. So we will get I naught square plus the RMS value of the fundamental component. So RMS value of the fundamental component is I1 by root 2 and we will square it. The fundamental second harmonic component is also there. So the RMS value of second harmonic component will be I2 by root 2 and we will square it. So this is how calculating the RMS values of individual component, and then if we square and add, and then if we take the root of all that addition, we will get the RMS value of this complete current, which is having so many other frequency component apart from the fundamental present in it. So this is how we are going to calculate the IRMS current. Now we have defined one thing, current distortion factor. So what is this current distortion factor? This we have defined yesterday, current distortion factor. Current distortion factor CDF, and it is denoted by G, and G is basically equals to the fundamental RMS component when divided by the total RMS component, we get the value of G. So this is how we have obtained the value of G, that is the current distortion factor. This is what we have derived yesterday, and this is how we are going to calculate the RMS value of a particular nature of current which is having so many harmonic component present in itself. Now what we have discussed yesterday, if suppose this is the current distortion factor, then we have discussed yesterday that the current distortion factor, we have discussed that in current distortion factor, ideally what should be there? Ideally what we want is this I1 RMS should be equal to the IRMS, means ideally there should not be any other frequency component present in the signal, isn't it? Ideally we want that only fundamental component will be there. So if other frequency component are 0, means there is no other frequency component, we will be getting IRMS equals to I1 RMS. In that case what will happen? In that case we will get the value of CDF to be equals to 1, isn't it? The value of CDF, that is G, in that case will be equals to 1. So ideally this should be the value of CDF, current distortion factor. So the current distortion factor is ideally having a value equals to 1, but practically what happens? Practically we are getting something else. So practically what we are getting is that IRMS, total RMS value of current, which when it is having multiple harmonic term, is basically greater than the fundamental RMS component. So due to this reason what happens? Due to this reason the current distortion factor, that is G, is having a value greater than 1, isn't it? What is CD? CD is basically, it will be having a value less than 1, because CD is what? CD is basically I1 RMS divided by I1 RMS divided by what? I1 RMS divided by total RMS component. So if IRMS is greater than I1 RMS, probably the G is going to have a value less than 1. So practically this is the case. Practically if the harmonics are there, then the current distortion factor will be having a value less than 1. But practically, ideally, this should have a value equals to 1, isn't it? And I1 RMS should only be equals to IRMS. This means there should not be any other frequency component, there should not be any harmonic component. That is what desired, but actually practically harmonics are there in power electronic converter, and due to that the current distortion factor has a value less than 1. So if I ask you a general question, what should be there for a perfect sine wave? Means if there are no harmonics, the perfect sine wave will have a current distortion factor value equals to 1, isn't it? So this is how we will analyze the AC side of the converter. So we have defined current distortion factor. So what is basically CDF? Current distortion factor, that is CG, is basically the fundamental RMS component divided by the total RMS current, and the value of G. The value of G ideally is equals to what? Ideally the value of G is equals to 1 when we have IRMS, fundamental component of current, is equals to the total RMS value of current. Means there are no harmonics, isn't it? No harmonics are there. But practically what is the case? Practically what we are getting is, practically we are getting the value of G equal less than 1 because the IRMS component is greater than I1 RMS, and the reason is harmonics. This is due to harmonics. Okay, so if the harmonics are present, we are getting a value of G less than 1. So now from here you can predict, as the value of G approaches towards unity, as the value of G approaches towards unity, the perfect sine wave nature of the waveform will be restored, isn't it? If suppose harmonics are not there, then the waveform might be having a perfect sine wave nature. But if the harmonics are there, waveform might not be having a perfect sine wave nature. It is a distorted waveform, and that is why we are calculating the current distortion factor. Because of harmonic, the distortion will be there, so the waveform might not be having a perfect sine wave nature. So if the waveform requires to be perfect sine wave, the value of G should approach to unity as much as close as possible. Okay, there should not be no harmonics in that case, but if the harmonics are there, G value will never be equals to 1. Now we may define another factor as well, which is known as the current distortion factor. So what do we mean by this current distortion factor? So this current distortion factor is basically THD, and THD is given by this formula 1 upon CDF square minus 1. Okay, on putting the value of CDF, we will get a formula. When we put the value of CDS to be this one, we will get IRMS square minus I1 RMS square divided by I1 RMS square. Now we may write the numerator like this as well. The numerator is basically, we are subtracting the fundamental component from the RMS component, so it might be equals to n equals to 2 to infinite IN RMS divided by I1 RMS square. So this is how we will calculate the total harmonic distortion. Okay, now what should be there? Ideally the numerator should be 0, means there should not be any harmonic component. So what is the value of THD ideally? So ideally the THD value must be equals to what? Ideally the THD value must be equals to 0, but practically this value is not equals to 0, and we will be getting some THD value. So practically this THD value will not be equals to 0, and we are forced to get some THD content, isn't it? Because of the harmonic. So ideally if I talk about, so ideally what should be the value of THD? Ideally if we are talking about the THD, means will be equals to 0, but practically THD will not be 0, and practically as per the IEEE standard, THD of 5% or less are allowed. Okay, so this is how the harmonics are going to affect the AC side of the converter. So if I ask you, if we want to have the perfect sine wave, then what are the values of CDF and THD in case of a perfect sine wave? The CDF value might be equals to 1 only fundamental component will be there, and the THD value might be equal to 0 only. Okay, now similarly, if suppose we want to analyze the DC side of the converter, So at the DC side, what do we want? At the DC side, we want only perfect DC voltage or current. But due to the power electronics converter or the switching action of the power electronic converter, we are getting some AC content apart from the DC as well, and that AC content which is not required, that multiple frequency AC content that we are getting which is not required, is called as the ripples. So we want only the DC component, but we are getting an AC component as well. So in order to analyze how much AC content is there in the DC content, okay, we want only the DC content. So if we are getting pure DC, that's absolutely fine. But in power electronic converter, we are not getting pure DC, we are getting some AC content imposed on DC as well, which is called as ripples. And ripples are nothing but the multiple harmonic component, multiple frequency component, and we are getting that as well. So we need to calculate how much that perfect DC is being polluted by the ripples, and that measurement is being done through the help of form factor and voltage ripple factor. So what is this form factor? So form factor is defined as the ratio of RMS value of the voltage to the average value of the voltage. Now, for a perfect DC, and this voltage ripple factor, let me define this voltage ripple factor as well. This voltage ripple factor, the measurement of the voltage ripples in the voltage in the DC is equals to the form factor square minus 1. Form factor square minus 1. So what do we want to have? We want to have a, see what we are getting at output. So we are getting at output this kind of voltage which is having the DC voltage as well, which is having the fundamental voltage as well, which is having second harmonic it might have, third harmonic it might have, or it might have any order of harmonic. What do we want? We want that our RMS value of this total voltage might only be equals to V0. But we are forced to have the other component as well, which are called as the ripples. Which are called as the ripples. We do not want these components to be present in the perfect DC, but we are forced to have these components present in the DC voltage. So if we are going to calculate the total RMS value, the total RMS value will be the sum of all the components. So this is what we required ideally. But practically, how we are going to get this RMS value? Practically, this RMS value is equals to basically V0 square plus V01 RMS square plus V02 RMS square and so on. So practically this RMS value of this voltage will be sum of RMS values of all the components. All the components will be involved in calculation of this RMS value. So practically this is what we are going to get. Okay, this is happening practically, but ideally we don't want other frequency component to be present there. So if I ask you, if suppose these components are not present here, then in perfect DC, what should be there? For a perfect DC means no ripple. If no ripple is present, in that case, our RMS value and average value, in case of a perfect DC, the RMS and average values are exactly equal, isn't it? So what will be the value of form factor? So ideally the form factor value will be equals to 1, because in case of a perfect DC, what is the nature of perfect DC? This is perfect DC. So in case of a perfect DC, the RMS and average values are exactly equal to each other, isn't it? The RMS and average values are exactly equal to each other, and the value of form factor will be 1. But practically what is the case? Practically if harmonics or ripples are there, then this RMS value is going to have a more value than this alone V0, isn't it? So practically we are getting VRMS, total value of RMS voltage is greater than this average value of voltage, isn't it? So practically what will be the value of form factor? So practically speaking, form factor is much greater than 1. A value of form factor which is equals to 1, that means the DC is not polluted, this is a pure DC. But if suppose we are getting the form factor value greater than 1, that means our DC is not pure, it is polluted. So ideally speaking, the form factor should have a value equals to 1. Now ideally speaking, what will be the value of this voltage ripple factor? What will be the value of voltage ripple factor? So if form factor is equals to 1, what we are going to get here? If suppose form factor is equals to 1, so ideally what we are going to have, ideally the form factor should be 1 and voltage ripple factor should be equals to 0. But practically what we are getting is, if suppose ripples are there, then form factor might be equals to greater than 1, and in case voltage ripple factor will not be equal to 0, means that DC is a polluted DC, isn't it? So these are the factor: voltage ripple factor, form factor. These terms will be used to analyze the ripple content, harmonic content on the DC side of the converter. Current distortion factor, total harmonic distortion, these are the terms that will be used to analyze the AC side of the converter. I have seen students confused related to these four terms, where they have to involve with which particular term. So if it is a DC side of the converter, then we are involved with voltage ripple factor and form factor, and if it is an AC side of the converter, we will be involved with current distortion factor and total harmonic distortion. Is it clear? Very good. Now, what is the definition of, in that case, for a perfect AC and a perfect DC? So if we are talking about perfect AC, a perfect AC waveform, so a perfect AC is something like this. So if we talk about perfect AC and perfect DC, then perfect AC might be having this shape and perfect DC is defined by this particular shape. So if it is a perfect AC, what should be the shape of that particular AC waveform? If suppose this is a perfect AC waveform, then this might be having this particular shape. Isn't it? It is free from any harmonic component. And if it is a perfect DC, this might be having this shape, a constant voltage, isn't it? So this is a perfect AC and this is a perfect DC having no harmonic content whatsoever. So in case of a perfect AC, if we are talking about no harmonic component is there, so a perfect AC is defined as, for a perfect AC, the current distortion factor term might have a value equals to current distortion factor, that is G, will be equals to 1, and we are having total harmonic distortion content equal to 0. This is the definition of a perfect AC, isn't it? If suppose the CDF value is not equals to 1, less than 1, THD will be not equal to 0, having some value, we will get a polluted AC which is not following the perfect sine wave. Okay. Now we're talking about a perfect DC. So if we are talking about a perfect DC, then what we are realizing here, for a perfect DC, the value of form factor will be equals to 1. Okay, let me write this here so that we can utilize this space. So for a perfect DC, what should be there? The value of form factor, this value is equals to 1, RMS and average values are exactly equal, and the value of voltage ripple factor is equal to 0. So this is the definition of a perfect DC voltage, isn't it? This is the definition of a perfect DC voltage. So for a perfect DC, the form factor is having 1 value and the voltage ripple factor is 0. No ripple is there. Now, as we have seen here, as the G value approaches unity, the nature of, let me write this point because this is a very important point. So as G approaches unity, the perfect sine wave shape perfect sine shape of waveform is restored. Of the waveform is restored, isn't it? Now, similarly, we can find a note here as well. So we can write here that as the form factor approaches unity, the perfect DC wave shape might be restored. Perfect DC waveform shape will be restored, isn't it? Let me talk about an example. Let us suppose I am drawing few shapes. So if suppose I am drawing a perfect DC waveform, this is a perfect DC waveform, so the form factor might have a value equals to 1. Let us suppose I am drawing this particular waveform which is having, is this a perfect DC? Not at all. This is just because of it is having a form factor value greater than 1. Let me draw this waveform, and in this waveform you can see this waveform is approaching very close to the DC waveform, and it is having a value of form factor quite close to 1, isn't it? So this is how we will define a perfect AC and perfect DC, and this is how we are going to analyze the harmonic analysis on AC side and DC side of the converter. So current distortion factor and total harmonic distortion, these are the terms restricted with the AC analysis on harmonic analysis on AC side of the converter. Voltage ripple factor and form factor, these are the terms restricted with harmonic analysis on the DC side of the converters. So let me ask you, this CDF THD term you might be calculating in case of the rectifier and in case of the inverters, but when it comes to the choppers, have you calculated THD and CDF? Just think about that. Okay, just think about that. So when it comes to the harmonic analysis of AC side of converters, CDF and THD are the terms we will be using. When it comes to the harmonic analysis of DC side of the converter, voltage ripple factor and form factor are the terms that we will be analyzing. So I hope these concepts are very clear to you. Now let me move towards the concepts of basic concepts of power semiconductor devices. Now we have signal devices in which we have a normal configuration, but in power electronics you might be dealing with power devices. So whenever you are just going through the structure of any power semiconductor devices, you might have gone through these terms. What is the meaning of P plus, P minus, N plus and N minus term? You might have seen the structure of the device like P plus, P minus, N minus, P plus. What actually that means? What is the meaning of this plus and minus? So these plus and minus holds for lightly doped and highly doped region. Okay. So if suppose we have positive, that means that indicates highly doped region. That indicates the highly doped region. If we have negative, that means the lightly doped region. Now exactly what it means? Now exactly what we mean by this? So just read this line. If suppose there is no plus minus signs are there and we are talking about a normal PN junction. In case of a normal PN junction, what will happen in case of a normal PN junction? Doping density in P-type junction will be equals to doping density in N-type junction. So if the doping concentration in P-type and N-type wafers are exactly equal, it is a normal PN junction. But if this doping concentration is disturbed either on P side or N side, one side might become highly doped or second side may become lightly doped. Let me discuss with an example. Let us suppose 10 to the power 17 per centimeter cube is the base concentration. Is the base concentration that we have. Now, looking into this concentration, let us suppose if we have framed a junction of P plus and N, then what does that mean? Or if suppose we have framed a junction of P plus N minus, or we can also frame a junction like P minus N plus type, isn't it? We may try on any of these combination. Then what it actually it means? So what is the base concentration that we have taken? 10 to the power 17 per centimeter cube. P plus means we are having concentration more than that. So let us suppose in this case the P side might be having a concentration of 10 to the power 19 per centimeter cube. And N side will be having, because no plus minus is written, so it is having exactly the same concentration. So this is what we have done here. If this is the base concentration, then P side is highly doped and N side is doped at the same level. So this junction will be called P plus N junction. Talking about this, if suppose P plus means if the base is 10 to the power 17, it might be having 10 to the power 19, 20, 21 per centimeter cube of concentration, and because N is negative, that means it is having lower concentration than that. So 10 to the power 17 is base, so it might be having 10 to the power 15, 14, 13 per centimeter cube of the concentration. So if this is so, this junction is called as the P plus N minus junction. Similarly, if suppose P minus is here, then this junction might be having 10 to the power 14 per centimeter cube concentration, and this might be having 10 to the power, because plus is there, 10 to the power 19 or 10 to the power 20 per centimeter cube of the concentration. So this is all this plus minus is what they mean about. Now, why we are changing this concentration? So see, if we have a lightly doped region on any side, that means it requires a large voltage to break down. Means if we have, you should note down this point, if suppose we have a lightly doped region at one side, then it requires a large voltage to break down. Let me write this point. So let me write this point. I will write here lightly doped region, at one side requires large breakdown voltage. Okay. So if we have lightly doped region at one side, that requires a large breakdown voltage. Let us suppose we have P plus N region here, then probably there is no, it does not require that much of large breakdown voltage. Let us suppose we have P plus N minus region. So we have a lightly doped region at one side, so it will require a large breakdown voltage. The junction will break down at a very large voltage. So ultimately it increases its voltage handling capability. Similarly, if we have P minus N plus region, again you can see there is a lightly doped region at the left side. So again the voltage at which this junction will break down will be very large. So if we have a lightly doped region at one side of the junction, it increases the voltage handling capacity of that particular device. Is that clear? And that is the reason we are converting signal devices into the power devices. So these many changes in their semiconductor physics we have to do. We are making those signal devices to handle very large voltage and very large current. So how we will make them like that? So changing their concentration level, changing the length of the device, and making the junction like that we have lightly doped layers. So what will happen? The length is increased, the lightly doped regions are there, so the device might be capable of carrying large voltage, okay, because the junction will break down right now at very large voltage. So this is how we will make normal devices capable of handling large voltages. Similarly, by doing so, we are also increasing the cross-sectional area of the device. So by increasing the cross-sectional area of the device may be able to handle large current. So just by increasing the length of device and cross-sectional area and changing the concentration, so that one layer might be having lightly doped region, so that the device might be able to handle large voltage and large current and ultimately large power. So this is what this P plus P minus N plus N minus is all that we mean. I hope this is very clear to you, and this is the general concept most of the students don't know, and they even go through these particular devices. Okay, now power semiconductor devices. So before actually getting into particular devices, we should understand how a normal PN junction works. We should understand how a normal PN junction actually works. So a PN junction is framed by joining P type and N type wafer together. So P type N type wafer, when they join together, there is a boundary framed. When it comes to P type wafer, in P type wafer we have holes which are present in very large quantity. So the concentration of holes in P type layer is very much. When it comes to N type layer, the electrons are present in a very large number. So the concentration of electron at N type layer is very high. Now if you see in P type layer, the holes are, this is holes, these are holes, and they are the majority carrier. The holes are the majority carriers. They are present in very large number. They are the majority carriers here, and this hole is attached with this acceptor ion. So this is here the majority carrier. This is here the majority carrier. Now these holes of P types are very mobile. They are ready to move very frequently, but these minority carriers, I have written majority, let me clear it. So these minority carriers which are very immobile. Okay, they are not ready to move, they are immobile, so they will not, very rarely is there any movement. So in P type, holes are present in majority. The concentration of holes are very large. Every hole here is formed as majority carrier because their number is so many here, and it is attached to some minority carrier which are immobile, not ready to move very easy. Similarly for N type, what we have in N type, we have electrons present in majority, and electrons are present in majority. This is electron, and they are the majority carrier in N type because their number or their concentration is very high. And we have these charges which are immobile or donor ions, we can say. These are minority carriers here. Minority carriers here. Okay. Now if suppose we are joining one P layer and one N layer, then what will happen? The current will be caused through two processes, diffusion and drift. Okay, these two words, I am calling these two words diffusion and drift. So what do we mean by diffusion and drift? I am calling two words, diffusion, and I am calling drift. So the current might be due to these two processes, diffusion and drift. Now what do we mean by diffusion? So if the current is due to the change in the carrier concentration, then that current is called as the diffusion current. So why this current is there? Diffusion current is just because of the change in the current carrier concentration. Okay, diffusion process. Diffusion current will be due to change in concentration. Due to change in carrier concentration. So diffusion process might be taking place due to the change in carrier concentration. Now this is a very important point that you should exactly note and remember. When it comes to drift, the movement is due to the applied field. Okay, so if the movement is due to, so here we will be having the movement due to the field. So here we have the movement due to electric field. So this current you will get to see when there is an applied electric field, and this current is due to change in concentration of carrier concentration. Okay, so diffusion and drift are the two currents which will be present here. So what will happen when we will combine these P and N wafers? What will happen? The holes will try to move to the N side, isn't it? The hole will try to move to the N side. The hole will try to move to the N side, and the electrons will try to move into the P side. Now due to their movement, what will happen? They will get diffused, and this boundary will be depleted due to their immobile side, because they are immobile, they are not ready to move. So whenever a hole is trying to be there at N type, and whenever an electron is trying to be there at P type, they will left behind the immobile ions. So these immobile ions get surrounded at the boundary, and they will form a depletion layer. So this is called as the depletion layer. Because this boundary is being depleted due to immobile ion, this layer is formed which is called as depletion layer. Now if you see, there is a space charge region at this boundary which will have an effect of electric field directed from this positive immobile ion towards this negative immobile ion. Now due to this electric field, the electrons of P type will get attracted towards the N type, and the electrons of N type will get attracted towards the P type. So there will be a movement of charge carriers due to this electric field as well. And when the charge carriers are moving due to electric field, the current is called as drift type of current. Okay, drift current. And here you can see, when electrons are moving towards there, and holes are moving towards electron, and electrons are moving towards hole, there is a change in concentration. So first we will get a diffusion current as well due to change in the carrier concentration towards N and P type. So this is how a PN junction will be. This is all about a PN junction when P and N type wafers are combined. So you get to know about these concepts: which type of carrier is majority carrier in P type, which type of carrier is minority carrier in P type. Similarly for N type, when it comes to P type, the electrons are minority carrier and holes are present in very great amount. When it comes to N type, the electrons are having excess, they are present in a very great amount. What do we mean by depletion layer? So there is a space charge region of immobile charges that will form a depletion layer. Okay, for silicon, the potential of this depletion layer is 0.7 volt, and for germanium the potential of this depletion width is around 0.3 volt. So in order the conduction to be possible, first of all we have to cross this depletion region, because once this depletion region is formed, this will not allow further movement of electron and hole from P to N or N to P type. So all these terms are you need to understand regarding a PN junction when no voltage is applied. Now we will see what happens if suppose we have forward bias a PN junction. So this is a PN N type wafer. Now let us suppose we have forward bias this particular PN junction. Forward biasing means we have applied positive potential at the P side and negative potential at the N side. So if we have applied positive potential at the P side, what will happen? The electrons will get attracted towards the positive positive terminal of the battery. So electrons, they might be moving towards in this direction, isn't it? They will be moving in this direction because they are attracted by the positive terminal of the battery. Similarly, the holes will get attracted by the negative terminal of the battery. The holes get attracted by the negative terminal of the battery. So positive terminal is attracting the electrons and negative terminal is attracting the holes. So there will be holes moving from P type wafer to N type wafer here. These holes might be moving from P type to N type because this negative terminal is attracting the hole. So the whole movement is from P to N type, and since the positive terminal is attracting the electrons, so the electron will move from N type to P type. So similarly, there will be a great movement, there will be a huge movement of electrons from N to P type, and there will be a very good movement of holes from P to N type as well. So you can see this is how the electrons and holes might be flowing in from P to N and N to P type. Now what is the direction of current? The current direction is exactly in the same way where the holes are flowing, and it is opposite to the direction where the electrons are flowing. So you can see here the electrons are flowing towards the positive terminal of the battery. So the direction of current will be opposite to the direction of electrons flow. So this is how the forward current will be flowing across this junction. Now mind here, before applying this voltage, there will be a depletion layer here. So this voltage that we are applying here, Vf, this has to be greater than 0.7 or 0.7.3, which is called as the cut-in voltage or knee potential. So if this voltage, applied voltage, is greater than this voltage, this depletion layer will vanish, and there might be a movement of hole from P to N type and electron from N type to P type, and this will cause ultimately the current. So when we are forward biasing PN junction, we are getting a current, we are getting the flow of current possible. What happens if suppose we have reverse bias our PN junction? So reverse biasing PN junction means we have applied negative potential at the P side and positive potential at the N side. So what will happen? This negative potential, this negative terminal of the battery will be attracting the holes. So holes will be flowing from the P layer towards the negative terminal of the battery, because negative terminal of battery will attract the holes. Similarly, this positive terminal will attract all the electrons towards itself. So if holes are attracted by the negative terminal of the battery, positive terminal is attracting all the electrons. So what will happen? This region, this boundary will be depleted more by immobile regions, isn't it? Because holes are right now moving towards the positive terminal of the battery, electrons are moving towards the negative terminal of the battery, and this boundary is being left by these immobile charges, isn't it? These immobile charges, the acceptor ion and the donor ion and the acceptor ions. So the donor ion of the N type will deplete the N type region, the acceptor ion from P type will deplete this particular region of P type. So this width of depletion layer will increase and increase, isn't it? So this depletion layer width, depletion layer increases, and depletion layer increases, and there will be a very, very low current called as minority charge carriers current, or very, very low current in nanoamperes might be flowing, or we can say there is no current in this particular case. Practically measuring current in ampere, there will not be, or milliampere, there will not be any current here. So this is what happens when we have reverse bias this particular junction. Now, if suppose the reverse bias current is there, then what will be the direction of reverse bias current? Since electrons are flowing in this direction, so the reverse current will flow in this direction. So there might be a current which is called as reverse bias current. IR might be flowing in this direction. Now, if you compare, the direction of IR is exactly opposite to the forward current, which we have forward bias PN junction might be flowing here. So reverse current has the opposite direction, so to that of the forward current is what we are having here. Okay, so this is how a PN junction will behave in room temperature, or when it is forward bias, or when it is reverse biased. Now, reverse recovery process. Let us suppose we are moving from here to here. Let us suppose PN junction or PN diode was conducting. It is conducting a forward current. Now let us suppose we want to move from that condition to this condition, means we want to switch off, we want to turn off the on PN junction into, we want to convert it from on stage to off stage. So let us suppose we were in this condition and we want to be in this condition, we want to turn off our device. Then what will be the process? That process we will study through reverse recovery process. So see what exactly will happen here. So before we have applied the reverse bias, what is the condition we are in? Before we have applied the reverse bias, this is the time t and this is the current here. So before we have applied any reverse voltage, we are having a forward current flowing, isn't it? We have the forward current flowing before we have applied any reverse bias voltage. Now what will happen if we apply the reverse bias voltage? So when we will apply the reverse bias voltage, our current IF will first get into 0 and then it will return to a current IR, and then if the reverse recovery process will complete, then it will turn out to be 0. Okay. So first what will happen? The IF current will return to 0 and then it will return to IR. Means suppose we are in this stage, first of all, where we have a IF current flowing, forward current flowing. Now we are moving into this stage, we are applying a negative voltage. We want to turn off our device. So first we will apply the negative voltage. Immediately what will happen? The current will reduce to 0. The current will reduce to 0. And then can you see here? There is a reverse current flowing as well. So reverse current is just opposite to that of the forward current. So we have one current flowing which is called as reverse current. So reverse current will be flowing and it will reach towards its peak, which is called as maximum reverse recovery current. Okay, so the current will reverse and it will reach to its peaks. Now what will happen when we have applied the reverse voltage? Earlier what has happened, some of the holes have crossed the junction and reached to the n type layer, and some of electrons have crossed the junction and they have reached to this p region. Now we have to recover back these electron and holes which have already crossed the junction, and then we can turn off the device, because if we are not able to do that, the device may again turn off without getting a proper voltage, isn't it? So during the turn on process, those holes which have crossed the junction and reached to the n layer, and those electrons which have crossed the junction and reached to the p layer, they need to be recovered as well. So earlier what we have done, right now we have applied a reverse voltage, so the forward current will first reach to 0 and then it will reverse. Now we have to recover those holes as well which are present here, and those electrons here which are present here. So they need to be recovered back as well, isn't it? These electrons and these holes need to be recovered back. So first what will happen? First of all, this when we will apply a reverse voltage, the forward current will become 0 and then it will reverse in the direction, and then it will start decreasing as well, and then when we will be having these charges recover, then ultimately the current will become equal to 0. So this is what is called as IRM current, and this total time which it has taken to become 0 is called as the TRR, where we have TRR being divided into two times. First is the TA, in which the current is reaching its peak, and then we have another time TB, in which the current reaches almost 1/4 of its value. Another time that we have is called as TB, in which the current reaches 1/4 of its maximum value. So we have this reverse recovery time here as well, which is basically equals to TA plus TB. TA is the time in which the reverse current reaches to its maximum value. TB is the time from maximum to 1/4 of the maximum time taken for the current to reach. Okay. So TRR, which is called as reverse recovery time, is basically the sum of these two times. This is called as reverse recovery time. So what will happen? First of all, the forward current, when we will apply the reverse voltage, will get into 0, and then there will be a current building in the reverse direction, and after that this reverse current will decrease, and finally we will get the current I equal to 0. So this is the process through which a semiconductor device will always get off. Okay, we will apply a reverse voltage. Earlier we have a forward current, then we will apply a reverse voltage, then the current suddenly reaches to 0, and then it will build up in the reverse direction. Then finally, when the reverse recovery is being done, what do we mean by reverse recovery time? So this is the time basically in which excess charge carriers what do we mean by excess charge carrier? Those charge carriers which have crossed the junction and reached to the other layer during the conduction down, they need to be recovered back. So excess charge carrier needs to be recovered back. So reverse recovery time is basically that time in which we are recovering the charge carriers, those have already crossed the junction and have reached to the next boundary. We need to recover them back. So this is the time taken to recover back them, isn't it? So first of all, when we are turning off the device, so what is the process of turning off the device? Process of turn off is what? First of all, you will apply a negative voltage. Earlier we have a forward current flowing, then this forward current will reach to 0, and then there will be a reverse current building up in the negative direction, and then after reverse recovery this current will reach to 0, and finally when the current becomes 0, we will say that the device is now turned off. Okay, this is the process when reverse recovery is happening. So this is how the device will get into the off stage. So any power semiconductor device, when we are turning it off from the turn on stage, the reverse recovery process is something that will be there, that needs to be there. Okay, now we may call this as the slope of this particular IR current, which is di by dt. Now we may approximate TRR to be TA only. We may approximate TRR to be TA only. Okay, so if we want to calculate the slope di by dt, then what it will become? The slope di by dt, this is basically equals to IRM upon TRR, isn't it? We may write this slope to be di by dt is basically IRM upon TA, it should be TA, but we have approximated TA to be TRR. So this is what we can write here. Now, during the reverse recovery time, let us suppose this is the charge stored. This is the charge store which will be recovered back. So if we want to calculate this Q will be what? This Q will be basically half into TRR into IRM, the area of this particular triangle, isn't it? This is a kind of triangle. We can approximate this to be a triangle. So what will happen? The area of triangle is what we need to calculate here. So now from here what we can say, what is the value of IRM if we want to calculate? So the value of IRM will be here di by dt multiplied with TRR. So this is what we are going to put here, 1 by 2 into TRR into di by dt into TRR. So if we want to calculate what is going to be TRR here, then TRR here will be 2q over di by dt. So this is how we are going to calculate the reverse recovery time here. Okay, so the reverse recovery time is basically equals to what? Under root of 2q upon di by dt. Is it clear? So reverse recovery process you need to understand very carefully. If we want to turn off the we turn off the already on device, then we have to apply the negative voltage. Then what will happen? The forward current will first come to 0. Then because of the negative applied voltage, it will reverse in the negative direction. And then when the already stored charge carrier, those charge carrier which have crossed the boundary and reached to the next layer, will need to be recovered back into their original position, and that process is called as the reverse recovery. Once those charge carriers are also recovered, then the device will come into the off state. So whenever it is any power semiconductor device, this reverse recovery needs to be done there, isn't it? Now let me ask you one question. In this process we are reverse recovering both type of charge carrier, isn't it? Here we are recovering what? Here we are recovering electrons from p layer and we are recovering holes from n layer. Yes or no? We are recovering here. We are recovering here electrons from p layer which have crossed the n layer and reached to p layer. Now they need to be recovered back to n layer. And we are recovering holes from n layer which have crossed which have gone from p layer to n layer. The they need to be recovered from n layer. So we are exactly recovering these two things. We are doing these two things. So now based on these facts, can you tell me one thing? If we need to recover both electron and holes, it will take a lot of time. But let us suppose we only have to recover only one type of charge carrier, whether it is an electron or hole, then the time taken will get reduced, isn't it? The time taken will get reduced. So what we will do, we will classify the devices into majority and minority carrier devices. So in minority carrier, what will happen? In minority carrier devices, the conduction is due to both the electron and holes. So if the conduction is due to both the electron and holes, then what will happen? Then the reverse recovery time will be more here, isn't it? The reverse recovery time will be very, very high. That means ultimately the T off time will also be very, very high. And ultimately the total time, that is T on plus T off, will be very, very high, isn't it? So if the time is more, then what happens to the switching frequency? What happens to the switching frequency here? So their reverse recovery will need a lot of time, and if the time is more, what will happen to their frequency, switching frequency? So switching frequency, which is 1 of T, so if the time is very, very high, the switching frequency will be very, very low. So minority carrier devices, they will give you a very low switching frequency. Examples can be, examples of minority carrier devices can be, examples of minority carrier devices can be diode, SCR, BJT, IGBT and GTO, triac. All the devices are minority carrier devices, isn't it? But when it comes to the devices which are majority carrier devices, what do we mean by majority carrier devices? So in majority carrier devices, the conduction is only due to electrons or holes, isn't it? The conduction is only due to electrons or holes, okay, not because of both of them. The conduction is only due to electron or hole. So when we are turning the device off, means when we are reverse recovering the device, then we need to recover either electron or hole, so their recovery will take less time, isn't it? So what will happen, the reverse recovery time will be very less here. So ultimately the T off time, the device turning off time will be very less, and ultimately the total time, which is T on plus T off, will be very less. And finally the frequency, switching frequency, which is 1 upon T, if the time is very low, then the frequency will be very high, so switching frequency will be more. So we can use these devices, majority carrier devices, up to that application that requires very high switching frequency, isn't it? So if we have this high switching frequency, we can reduce the ripple content, harmonic content, that is the advantage, okay? So what are the examples of majority carrier devices? So the examples of majority carrier devices are MOSFET. In MOSFET, the conduction is due to electron only, or metal semiconductor junction, like Schottky diode. So these all are the devices that are called as majority carrier devices, okay? So this is the concept of reverse recovery and how it is a very deciding factor, because it is ultimately affecting the switching frequency, isn't it? So this is what you should know. Now we have discussed all these concepts. Looking into these concepts, now we are able to describe power diode. So how normal signal diode can be converted into power diode? Just see, in normal signal diode we have only P and N type wafer combined together, isn't it? Now it has a very low voltage, current and power rating. But when it comes to the power diode, can you see here, there is an extra layer N-1 imposed between the P and N layer. This layer is called as the substrate. So substrate is that particular layer over which all other layers are being laid off, okay? So an N plus layer is the substrate layer over which we will put N minus layer, and over which we will put the P plus layer. So we have added this extra layer. Now can you see here, we have increased the length of the device, okay? So by increasing the length of the device, by increasing the length of the device, and inserting this extra N minus layer, okay, what we have done, we have made this power diode capable of handling large voltage, isn't it? Can handle large voltage, okay? So we have increased the length of the device so it may handle large voltage. Also you can see there is a P plus N minus layer here, so the breakdown will occur at very large voltage. Breakdown of this junction will occur at very large voltage, isn't it? So this is how this device is capable of handling large voltage. And by increasing the cross sectional area, the device is capable of handling large current as well. large current as well. So now this power diode, this can handle very large voltage and current. And do you know the power diode, they are available in they can handle even 5000 volt of voltage and 2000 ampere of current. So just by modifying these particular changes, we have made our device capable of handling that much amount of voltage and that much amount of current. Okay, but since there is no control terminal, so diodes are uncontrolled semiconductor switch. Okay, they will not provide any control if they are used in a particular application. Okay, also the cut-in voltage in signal diode, what is the cut-in voltage? Normally it is 0.7 volt, but when it comes to power diode, the cut-in voltage may be as high as 1 volt as well. Okay, and what is the reverse voltage handled by these devices? If suppose the reverse voltage handled by power diode is VBRM. Okay, this is the reverse voltage handled by these devices, and suppose reverse voltage handled by these devices are only VBR, then what will be the value of reverse voltage across these devices? They are capable of handling more reverse voltage than the normal diodes. Okay, that is why they are called as the power diode, isn't it? So just by increasing the length and cross sectional area and modifying the concentration of layers, what we have done here, we have made normal diode capable of handling more voltage and current, and this device is being made now a power device. So these all are the concept, basic power semiconductor devices concept that we have discussed. So here you can see this change and how basically what is reverse recovery characteristics and how it is going to affect the switching frequency of majority and minority carrier devices, what we actually mean by reverse recovery process. And reverse recovery process is a very essential process, this has to be there. And after that, before that, we have discussed a reverse bias junction, a forward bias junction, normal PN junction. What do we mean by P plus P minus N plus layer? You need to understand that. And what is the nature of perfect AC and perfect DC? So when we will be using these terms like THD and CDF, and when we will be using the terms like VRF and ripple factor, form factor. So all these fundamentals we have discussed right now. Now when you will reach into the actual topics, you will not be having any problem in understanding the concept behind calculating CDF, THD, VRF and form factor. And now you will get to know what is meaning of perfect AC and perfect DC. You have also got to know about the semiconductor physics and some important points related to some semiconductor physics as well. Now when you will go into the actual chapters, you are going to rock and you are going to enjoy those lectures. So this is all from today's lecture. We will meet in the next lecture and we will discuss some other fundamental concept related to subject power electronics. So I hope you have enjoyed this lecture. Thank you so much for being there.